Somebody knows something about it. Nothing? Have you heard that term before? And you have nothing, you associate nothing with it?
People crying about it.
People crying, mostly? A lot of crying in organic chemistry. Yeah, okay, that's fair. There's nothing wrong with crying, right? It's an important part of life, important thing to do. But it's true that maybe you want to minimize chemistry-related crying, I don't know. But anyway, yeah, organic chemistry has this reputation of like this really hard thing to do. That is a little bit earned and a little bit not, depending on how we go into it. I will tell you this, I don't think it has anything to do with the subject itself. I don't think there's anything inherently frightening and difficult about organic chemistry compared to all the other stuff we've done this semester. I will say that it's a little different, but that can be good and bad. Like if you've been struggling with some of the math stuff throughout the semester and some of the like complicated problems where you have to pick out numbers, that kind of thing, we don't have any of that here in organic chemistry land. Organic chemists can barely add. So, you know, I'll tell them that later. But yeah, there's not a whole lot of that here. So some people really like that. I like that. Organic chemistry was the class that made me want to go into chemistry in college because I was like, oh, mole calculations are stupid and boring, and this is actually interesting and fun. So I like this better. But it does depend a lot on how it's taught. And if you end up taking a full organic chemistry class, it can be done in a couple different ways that can either be scary or not, depending on how your brain works. Some people get very frustrated about organic chemistry because it requires things like spinning shapes around in your head and a lot of really complicated visual and, is there like a name for that? Does anybody like have teacher education background? I don't know. Is there a name for like being able to deal with shapes in your head and think about things in 3 dimensions? I don't know. Do you know what I'm talking about though, kind of? Or those questions where it says like, here's an object, what does it look like on each side, that kind of thing. There's a lot of that sort of thing in here. So we'll see how that goes. But anyway, in this class, I don't think you need to be afraid of this. We only got a couple weeks anyway, right? Can't be that bad. So let's define it first of all. Organic chemistry is the chemistry of misspelled words of molecules made primarily of carbon, hydrogen, oxygen, nitrogen. And there's other stuff in organic molecules too, but we're saying this is the chemistry of molecules made primarily out of these things. Primarily out of these things. Why does it have the special name organic? What does that word mean to you, like outside of a chemistry context? You've probably heard that word before. What does organic mean in general?
Naturally occurring.
Something about naturally occurring or yeah. And that's where the term comes from initially or originally. So before we knew that much about molecules and things, the idea was that you could either have chemistry that came from life, like molecules that were produced by living things, or molecules that were part of the earth, that were non-living things. So you had your organic chemistry and your inorganic chemistry. And for a long time, it was thought that they were completely separate. There were no compounds from life that existed outside of living things. And there were no minerals and earth type things, inorganic things that were found in living things. And now we know that's not really true. There's plenty of crossover. You can make organic compounds from inorganic compounds and vice versa. So you can take like mineral nitrates and things like that, and you can turn them into amino acids, which then can build up molecules for living things and all of that. So we know that like chemistry is chemistry and there aren't these two separate domains, but the name's still stuck. It's just now we say it's just this kind of chemistry, these kind of molecules. And it still makes sense to call it like the chemistry of life or that kind of a thing, because what's special about those atoms is when they join together, they do make up the molecules of life. So like all the stuff we're made of, the proteins, the, well, not water, but like all the other stuff, the cells, the enzymes, all that kind of thing, carbohydrates, whatever, fats, that's all made out of those kinds of things. And they're all based on carbon. So it makes sense to kind of call this the chemistry of life also. Okay, so to get in this a little bit, we have to then focus on carbon and talk about what it looks like, what its structure looks like, what a carbon-based molecule does, and how that's going to be different from other stuff or the same as other stuff. So let's go back a couple chapters and review how many valence electrons does a carbon atom have? 4, yeah. So if we got 4 carbon atoms, how many bonds does it want to make? Or 4 carbon electrons, how many bonds does it want to make? 4 also. Why 4 also?
Because it wants a full outer shell.
Yeah, because you want 8 electrons in the outer shell. That's what we call a full octet or a full shell. Remember when we kind of built those things up a couple chapters ago? So we've got basically 4 positions where we can't attach other things and share electrons. And the simplest organic compound comes from mixing those with 4 hydrogen atoms. Each hydrogen atom has an electron and then an open spot where it wants to bond because it needs 2 electrons to fill up its bucket, right, to fill up its shell. So that's not HO, by the way, that's just H with a little, we'll do it like this or something. Okay, so those all come together and you end up with this. Right? We've looked at this compound before, I think. Each bond is a pair of electrons shared between carbon and hydrogen. And then the way we usually draw that is not with the dots, but with lines instead. And one line represents 1 pair of electrons shared between carbon and hydrogen. All right, so that is the smallest organic compound, and that's called methane. 1 carbon and 4 hydrogens. Now, that's a fine way of describing how it's connected. Carbon atom in the middle and 4 hydrogen atoms connected to it. But it's not actually an accurate way of representing the structure of methane. So the way that we've drawn this, what's this angle here? It's not your question. Yeah. This is not the real angle. For a methane molecule. And I don't know why these balloons are in here, but they work for this, so I'm just going to use them. We'll pretend that I brought them because I'm well prepared for class. All right, so the way we've drawn it is kind of like this, right? And if you notice, I kind of had to like squish the balloons to fit them into that position. If we just let them do whatever they want, it goes more in that position. And that's a different shape, right? That's a different kind of an angle. It's kind of a 3-dimensional shape, one that we've seen a little bit before. And that's more the real shape of that. And it's because of exactly what we did, that big things like electrons or atoms want to get as far away from each other as possible. They want to spread out and have enough space. So when we force them to get closer than they want, there's some repulsion there. And that leads to an instability. So they're going to be much more stable if we just kind of let them do what they want and get in the most space possible. Okay, so to show you what that looks like, rather than trying to draw it first, let's use our fancy technology of the future and draw it like this. So I'm going to make a carbon atom in the middle with 4 hydrogen atoms around the outside. And that gives me this type of a structure. I'm just going to let that spin a little bit. So that's the more correct structure of methane, and that's actually exactly what these balloons are doing. You've got the carbon atom in the middle, and then you've got 4 equidistant hydrogen atoms that are that are spread out at these particular angles. So if we go right here, what do you think about that bond angle? Do you think that's bigger or smaller than 90 degrees? What? It's bigger. Do you see how it's wider than straight? So that tells us that this is a better arrangement for the hydrogen. It allows them to be further apart. They're not as squished together. And this particular arrangement is called, I'm just trying to get in the right position here, is called tetrahedral. We'll write that down in a minute. Let me copy this over into our notes. We call this tetrahedral geometry. And that angle is actually more like 110 degrees. So a bit more spread out than the 90 degrees we would think. Okay, so if we want to write this on paper, I don't know, some of you are probably good with your 3D drawing skills and stuff. I'm not great, but we have some conventions to help us with this. So the way we draw this in 3 dimensions is we write that carbon in the middle, and then we say, well, okay, this could be flat. There's really just 2 atoms that are messing it up for us. So this atom and this atom and this atom are all flat. But then this one's kind of coming out at us, and this one's going back away from us. That's what's kind of giving us trouble in the 3-dimensional structure here. So we use regular straight lines for the ones that are in the regular plane of the screen or of your paper. And then to show that one of them is coming out at us, we make this kind of triangle shape that's filled in that we call a wedge. And then the one that's going back, we use a kind of slightly triangle-shaped dash or hash. And that is supposed to show the same type of a structure. That's supposed to show that 3-dimensional part of the structure there. So this is what we would call dash wedge notation. And that's a better picture of the 3-dimensional structure of methane. All right. So that said, we're going to use both styles of writing. We're going to use the 3-dimensional dash wedge when we want to express 3-dimensional things, but we're also just going to use that regular grid one. What's important is just that we keep in the back of our heads that we know the actual structure is the 3-dimensional one, even if we're drawing them based on non-3-dimensional type structures. Where that word comes from, by the way, that tetrahedral, if you connect all the hydrogen atoms you get this shape that is basically a pyramid with a triangle bottom, so that every side is exactly the same, like a 3-sided pyramid. And that shape is called a tetrahedron. And in this picture, then, the carbon atom would be right in the middle of the tetrahedron. And then the hydrogens would be on each corner. So that's where we get that word tetrahedral geometry. Okay. So what we're going to do next is we're going to make a little table of the simplest organic compounds called the alkanes. And I'm going to start with a couple, and then I'm going to give you less and less information. You're going to construct the rest of it yourself once you get a sense of the pattern. So let's title this first. Let's say we're talking about alkenes. Nope, not alkenes, sorry. We'll get to those next. Alkanes. Yes, they are different. Alkanes are molecules made of only carbon and hydrogen. With all single bonds. So carbon and hydrogen connected only with single bonds. There's going to be multiple carbons, multiple hydrogens, but only single bonds. And we're going to build up from smaller to larger. So for each example, we're going to have a molecular formula. We're going to draw a structure. Leave a little room for that one. We're going to name it. And then we're going to draw something called a condensed structure, which is kind of an easier way of drawing it. And I'll show you how to do that. So the first member of our list is going to be the one that we just did, which is CH4, structure we just did. We'll also draw the three-dimensional structure here. And you'll see how that changes a little bit for the larger ones. The name of this is methane. And it doesn't really have a condensed structure. It's just kind of CH4. You'll see how the condensed structure works in the next one and future ones. Okay, next group, C2H6. This one, we're going to show two carbons connected together like that. And then carbon always needs 4 bonds. So the remaining hydrogens are going to go around the outside. So that each carbon has 4 bonds. A three-dimensional version of that might look like this. So this is going to be 2 tetrahedron connected together. And just to make it easier, we usually stick the straight line bonds in the middle so that we can make the dash and wedge come off the outside. Makes it a little bit easier to look at that way. We got that. If we go back to this, I can add another carbon on to this guy, this thing, and we see that same kind of structure. So you've got 2 carbons here, hydrogen coming off on straight bonds, and then hydrogen going back and forth here, just as we've drawn it. This one's called ethane. And its condensed structure, I'm going to draw first, then we'll talk about it. CH3, CH3. So look how that's different from the formula. The formula just tells us the overall count of carbons and hydrogens. It doesn't really tell us how things are connected to each other. The condensed structure gives us a little bit more information because it tells us there's a carbon with 3 hydrogens on it and then another carbon with 3 hydrogens on it. So the way we build a condensed structure is by taking all those hydrogens around the outside and condensing them down onto the carbon that they're connected to, and then writing it kind of in a straight line. And as you'll see when we get into more complicated structures, the condensed structures aren't always just a straight line like that. If you have different branching things, you can branch the condensed parts around. It's just about putting the hydrogens down on the carbon and listing them after the C so that we don't have to draw them all out every time. Okay. The next member, uh-oh. Glad I just saved it. Let's try that again. I don't think this computer likes being recorded and all these other things running at the same time. Okay. Can I restore it? Oh, okay, great. Okay, looks like we're back. Okay, the next member of the group is called propane. Its formula is C3H8. And now here's where I'm going to stop and ask you to fill in the rest of it. So can you draw a structure and a condensed structure for propane given just that information? All right, got some structures. So if you saw me do it in the previous one, I think the best way to write something like this is to always focus on the carbon chain first. So go C3 is going to be 3 carbons connected together, and then we can fill in the rest of the hydrogens. So that's going to be here, here, here. And there. 3-dimensional again would be you can either go down, up, or up, up, but you got to keep that kind of zigzag geometry. And then that condensed structure, if we can collapse the carbon or the hydrogens onto each carbon, we see the first carbon has 3 hydrogens attached to it, the second has 2, and then the third has 3. So the condensed structure will look like CH3, CH2, CH3. And then for the last one on the table here, I'm just going to tell you that this one's called butane. And see if you can do all the rest just by following the patterns. How many carbons, how many hydrogens, what do the structures look like? All right, so what could you tell based on the pattern that the structure of butane is probably going to have in it? 4 carbons. So we'll make a line of 4 carbons. Right, and then if we need every carbon to have 4 bonds, that requires 8 hydrogens. Sorry, 10 hydrogens, thank you. So that overall formula then is C4H10. With the dashes and the wedges, yeah.
Does it matter, like the exact order where you put the dashed ones in the?
No, I was just gonna say that. Yeah, it doesn't matter. Those are assumed to be right on top of each other like this, because if we look at that structure, so let's make a 4 carbon thing here. If we look at this structure and we put it in that position where it's perfectly zigzagged, hold on, just trying to get this in the right spot here, like that. Those dash and wedge ones would actually be right on top of each other, so it doesn't matter which side you write which one on. Just the only thing that matters is they got to be next to each other, because they are right next to each other. So we're assuming that they're right on top of each other, but we're drawing them as being off a little bit. Does that answer your question?
Yeah.
And then the condensed structure for that is going to be CH3, CH2, CH2, and CH3. All right, so that's our first 4 alkanes. And I don't know if anybody noticed this. Did you have a question? I don't know if anybody noticed this, but there's actually 2 ways to make butane that are not the same molecule. Let's put that up like that. I assume everybody who wrote it pretty much wrote something like that when you wrote your structures. There's another way to do it. So to figure that out, we need to think about the chain a little bit more as well. So let's just focus in on those carbons, those 4 carbons in a chain. Now we've already established that the actual angle that those are connected at doesn't really matter because they're not really in a straight line anyway, they're in a zigzag. So that means that it does not matter how you write the angles of those carbons, they all mean the same thing. So whether you go like that or like that or like that, those all mean the same thing. They all represent 4 carbons connected in a row, one after the other. And then they all have the same numbers of hydrogens. So like 3 on the end, and then 2 on each of the ones in the middle, and then 3 on the end again. So those are all the same structure, and bending or twisting the bonds doesn't change anything. Single bonds can rotate. They can spin around. We can flip them. So like if I take this structure and flip this one over to this side like that. This tells me, oh, it actually flips it back for me. It's the same kind of structure. I wonder what happens if I do it over here. I don't even know if I can do it. Yeah, I don't think it's going to let me do it. But anyway, no matter how we flip these things around, we've got the same structure. Maybe I don't have the right thing here. Here we go. So I flip this thing over here. It looks funky, but it's the same structure. I haven't changed any connections. And if I stretch it back out again, it'll kind of stretch itself back out. If I move it over, back over here somewhere, it'll figure out where the right place is to be again. All right, so those are all the same. So then how can we come up with another molecule that's still C4H10, that still has the same stuff, still the same material, that still follows the same rules of bonding, 4 bonds for carbon and 3 for hydrogen, or and 1 for hydrogen, but that is actually a different molecule that's connected differently? Can anybody come up with something? See if you can draw something. What might it look like? So draw a different structure using the same materials. 4 carbons and 10 hydrogens. Carbon can only be bound 4 times. It has to be bound 4 times. Hydrogen has to be bound 1 time. Did we find one? Nobody's confident about it? The key to finding a new molecule like this out of the same materials is, rather than like thinking about bending and twisting things, since we know that's all the same, think about breaking and reforming. If you could take a piece off and put it on somewhere else, then you've made something new. And that's what happens here. If we can break the end carbon off and stick it on in the middle instead, we've got something like this. And that's now different. So let's fill in the rest of the hydrogens, because we need 4 bonds on each carbon, and make sure that we have the right number of things. So if we count all that up, that is 4 carbons and, once again, 10 hydrogens. So we've got it. This is called an isomer. An isomer is a compound with the same formula but different connectivity, meaning the atoms are connected in a different way. So it's the same formula, but the pieces are connected in a different way. And it's got to be completely connected differently. So in a way that you can't just twist it around and make the same thing again. You actually have to break it apart and form a new bond in a different way. If we go back to the to our structure here, so if I, oops, if I get rid of that one and put it on here, we now have a different structure. And no amount of twisting or whatevering can make that have the same structure once again. So you see that? Okay. So that's called an isomer. And isomer describes a relationship. So you would say two structures are isomers of each other. It's not like this is the structure and this is the isomer. They are isomers of each other. All right, so let's practice finding some of these isomers. For our next piece of the table, instead of saying this is pentane, here's the structure, all this stuff, we're going to try to find the isomers of pentane. These are structures that all have the formula C5H12. There are 3 different isomers. Butane had 2 different isomers. Pentane has 3 different ones. See if you can come up with them without looking them up. Talk to the people around you or just try it. And then when you think you've got one, come draw it up on the board up here. One of them is, well, I'll let you go. There are 3 different ones. One of them should be pretty obvious. The others might be hard to find. Sure. Anything you think you've got, go ahead and put it up. Part of the goal of this exercise is not to just get the correct ones, but to get a bunch of different structures and then all talk together about which ones make sense as isomers and which ones don't. So if you have anything written down that looks different from something that's up there, please go ahead and put up whatever you've written. I will not point at you and say, yours is terrible or something. I don't know whose this is. All right, not saying if these are right or wrong, but there are still more that we can put up there. Anybody have anything different from what's up there? Do we have anything else to put up? Nothing? All right, get another chance. We'll just go to the next one. Okay, so we got 4 structures here, and I told you there were 3 different isomers. And that means that a couple of them, at least, assuming we got all of them, must be actually the same or somehow else not a correct structure for C5H10. So if you look at those structures, do you see anything that seems like it doesn't fit, or can you pick out 2 structures that seem like they might actually be the same? You find some?
The first 2 can be the same one
The first 2 can be the same one. How do you know?
because it's still like one long chain of carbon. So
It's just fun.
it's just the 2 are that like twisted around.
Yeah, so if we look at these chains here, and this is a good way to evaluate whether you have the same thing or something different, is look at the longest chain that you can make of connected carbons, regardless of how it bends. So like this one here, the longest I can make is 3, whether I go this way, or I can even do something like this. But 3 is still the longest number of carbons I can make. This one over here, again, I could go like this way, or I could go this way, because bends doesn't matter. Either way I go, the longest one I make is 4, and then I have 1 carbon coming off of the second number of the chain, the second carbon of the chain. So that's a good way to help determine which ones are the same and which ones aren't. So those 3 are the ones that we would say are the 3 isomers. I'm going to write them in condensed form. You can copy them in the full form if you want. I'll write them in condensed form. So in condensed form, that looks like this. The chain one, we can just kind of write like this. The other ones, it makes more sense, I think, to leave the lines in there to show the branching off. There's a way you can do it. We can talk about it, but I think it makes sense to just do it this way. All right, so you see how those are different, even though they all have the same formula? So those of you who came up with some of this stuff, what did you do? I guess, what were those of you who came up with any of these, even if you didn't post them, what did you do to try to figure out what the different structures were?
Think of something new without bending it.
Think of something new without bending it? So like taking things off and sticking them on other places, that kind of thing? Yeah, that's right. So I should also note, this is a difficult problem. I would not ask you on an exam, draw all the isomers of some formula, because it's hard to get all of them and make sure you're not missing anything. There's not really a good way to systematically, I mean, there is, but it's difficult to systematically go through and find them. What I might ask, though, is draw 2 of them. Draw 2 isomers of a certain formula, or draw 3 if there's, a bunch of them. So to practice that, and because I think this helps us understand what structures are the same and which ones are different, we're going to do the same activity, make it a little bit bigger. And we're going to do isomers of hexane. Hexane is the name for the next size of alkanes, which is the C6H14 structures. And there are 5 of these. So same thing. I'm going to erase these, and whenever you feel like you have something, put them up here. Even if you're not sure, or if you think yours might be the same as another one, the more structures we get, the better, so we can have a good discussion about which ones are the same and which ones are different.
You said there's 5?
There are 5, yeah.
These 2 packages will be able to rotate it up like the
I see lots of good structures, so go ahead and start posting. See if you can find them all.
We've got some more. There's plenty of markers. You can come up here if you want to. All right, so we got 5 structures up there. Are they all different? Well, there's still room for some more. So who's got some stuff that's not up there yet? Anybody? Well, thank you to those of you who put those up there. This will give us a good start. Let's see if we can go through these and see which ones maybe have some issues or are the same as other ones up there, and then that might point us toward where we need to go for the rest, or maybe we've got them all. We'll see. So who sees any issues with any of these structures? Either don't seem right, or they're the same as another one. Anybody see anything?
The first one up there has H3 on the ends, but it can't be H3, right?
Yeah, let's fix these. So we'll leave the structure intact because there's nothing wrong with the basic connectivity, but carbon always needs 4 bonds total. So it's got 1, 2, and there's only room for 2 hydrogens instead of 3. And same thing on the end here. Carbon needs 4 bonds, so if it's got 1, it needs 3 more hydrogens to make 4. So we got to change that to a 3. This is and the same thing on this side. This is a common mistake with the condensed structures. You have to always keep that in mind about carbon having 4 bonds. So sometimes it's more helpful to draw them in this type of a form, and then once you've got everything laid down, you can condense the hydrogens and make your condensed structures. Anybody see anything else? Yeah.
And that one, the carbons on the ends don't have.
Right, so we've got carbons here with 3 and 3, and then the carbons in the middle have 6 bonds instead of 4. So all we have to do is reorganize some hydrogens and fix that. We can take a couple of those off and put them on over here, and then take a couple of these off and fix the ends, but the structure can still stay intact. All right. So now I think all the structures look okay from a 4 bonds to carbon type standpoint. Does anybody see similarities? Do we have any repeats here, or are those 5 unique structures?
That one and that one.
Yes. Yes. All right. So this one is a line of 4 carbons with a carbon coming off of the second one in and a carbon coming off of the third one in. Can you see that? That's how we can describe the connections there. This one looks a little different, but we can really describe it the same way. It's a line of 4 carbons connected in a row, and then there's another carbon coming off of the second one and coming off of the third one. So even though that one's kind of twisted around, if you imagine stretching this out and like twisting it, you could turn this into that one. If you like pull this down like that, so pull this one over here, pull this down there, and then flip this one over, you got the same thing as that one. So those two are the same. Let's check out some of these other ones. Let's find the longest chain. So here they're all just in a row, so that's a chain of 6. That's our basic straight chain hexane, even though the ends are bent, that's fine, means the same thing. Down here, the longest chain I can find is 4. So that puts us in a little bit of danger of thinking that it might be the same as one of these 4s. The difference here is now carbons are connected both at the same carbon. See that? This carbon's connected here and this one is connected here. Whereas this one over here, they're on different carbons. So that's good. That tells us that's something different. And then this one, we've got a 5 carbon chain, 5 connected carbons, with 1 more carbon coming off of the second one in from the end. All right, so we've got 4 out of the 5 structures since these two are the same. That's pretty good. So look at your structures that you've drawn. Does anybody have one that is different from those?
It's a 5 carbon chain, but it's coming out of the middle one.
Okay, so kind of like this. So you take 5 carbons, and then you put one like that. Is that what you're saying? Okay. Yeah, that's the last one. So that's different because it still has a 5 carbon chain, but now this one is coming off of the middle instead of the second one in from the end, as it was the other. And I should also note, this like lining up of C's is a great way of setting it up and kind of trying to discover new structures and things like that. But when you actually draw a chemical structure on paper or whatever to record it, you need to have the hydrogens in there as well. So whether you do that in a condensed form or whether you draw it all out is up to you and up to whatever it says in the question, if it's a test or something. But the hydrogens need to be accounted for. So those are our 5 isomers of hexane. I'm going to draw them up here so we have them, because then next class we're going to name them all. So we've got our straight chain one. I'll just leave that one all together like this. We've got the one right below it, which is the chain of 4. We've got the other chain of 4. The one where we had 2 that were the same, and then we've got the 2 based on chains of 5. All right, like that. And that's our 5 isomers. So like I said, it's a really difficult problem to say, come up with all of the isomers, especially if I don't even tell you how many there are. That's really, really tough. But I might ask you write down 2 or 3 isomers of different isomers of hexane. I think that's fair. And I definitely would ask you, and there's some practice in your book and the homework for this too, if you look at 2 structures, can you tell if they're the same or not? Can you tell if they're the same, if they're isomers, or if they're completely unrelated, like they have different numbers of carbons or something like that. So that's really the important part of this exercise. Can you look at structures, play with them a little bit, manipulate them in your head, draw on them, whatever you need to do to figure out if two different structures are actually the same or different, or if they're isomers or not. So that's really the main skill that we've worked on here. All right, so on Thursday, we will continue with this. We'll talk about naming. And at the beginning of class, we'll have a quiz on nuclear chemistry from last week. So let's go do some nuclear chemistry upstairs.